Hi everyone, welcome back. In our last video we went through a couple of examples where we found the electric fields due to uniform charge distributions. In each case it was a rod of length L and charge Q. In the first case we had the charge distributed uniformly along the rod, and in the second case it had a functional distribution where the charge density was proportional to the distance from the right end of the rod. In this video, we're going to turn our attention to finding the electric field due again to, in this case, a uniformly charged rod, but at an arbitrary point in the xy plane instead of just along the axis of the rod. And then we're going to turn our attention to finding the electric field due to a curved rod, and that will get us ready to discuss finding the electric field due to a surface, which we'll hit in the next video, but not this video. So in this case, find the electric field at any point xy due to a uniformly charged rod on the y-axis centered at the origin. So the distribution is uniform, but this is actually more difficult than the last example in the previous video where we had a non-uniform distribution, because the integral is not symmetric and we're at an arbitrary point in the xy plane, not just on the x-axis. Now, here's the situation. We have a point, random point xy. Xy can be any point. They can be positive, negative, both, neither, etc. And we want to make sure that our solution works as long as xy is any point. So let's consider the electric field contribution, the electric field element, due to a random charge element, which I have colored in purple. So it's a charge that is on this rod. In other words, I've divided this rod up into a whole bunch of little bitty pieces, each of with dx, or if you will, dx prime, since I'm renaming my axes, since my point is xy. So how much charge is there? Well, the amount of charge there is equal to dq. Well, I know the electric field due to a charge dq. That's just going to be k dq over r squared. The electric field vector is going to be k dq over r squared times r hat. Well, in order to figure out what that unit vector is, I need to write out first what my actual vector is going from my charge element to my point in question. So since our unit vector will be kind of cumbersome to write out, we're just going to include it in the expression. And again, even though our analysis is going to go for the first quadrant, it turns out we will be able to generalize our result to all quadrants. So here's what we've talked about so far. In other words, there's the electric field element due to the charge element, and I've plugged in the fact that my unit vector is just equal to the actual vector going from the charge element to my point in question divided by that vector's magnitude. It turns out it's going to be a little bit easier for us to do it this way. So how much charge is there? Well, dq, it's a linear charge density, so that's going to be lambda dx, or dx prime. And lambda, that linear charge density, since it's a uniformly charged rod, it's just a constant, q divided by L. Now r, that's the distance from our charge element to where we're trying to calculate the electric field. Well, that's equal to the square root of the x distance squared plus the y distance squared. Well, the y distance is easy. That's called y. The x distance, well, we go down here, we're at the point x, but we're looking for it at the point on the rod x prime, so the x distance is x minus x prime. So Pythagorean theorem, that the overall distance is square root of x minus x prime squared plus y squared. So now we can plug in for our r and for our vector, our r vector. So again, all we've done is we've just plugged into our dE expression up here. We plugged in what r hat is. It's r vector divided by the distance from the charge to the point, the field point. So up here is our r vector. And notice that when we divided by our distance in our unit vector, that gave us an r cubed. So there's r, and now we have cubed it. Okay. Now, how do we go about integrating this? Because after all, the electric field vector is equal to the sum of all of the little bitty d electric field vectors. So we slap an integral sign in front of it, and we work it out. So this is not a trivial integral, at least not unless you have some recent practice in a lot of BC calculus or calculus 2 types of integration. But if you have, then it turns out to be an easy integral in principle, but messy to evaluate, as we're about to see. Now, before we move on to actually trying to evaluate the integral that we'll evaluate once we slap an integral sign in front of our dE, let's check to see whether our expression even makes sense. Does it pass a reality check? So let's consider it seems to make sense certainly as long as x is greater than, x has a value greater than the rightmost point on the right edge of the rod. But what if x is somewhere kind of above the rod? So let's consider the situation where our x value for the field point is, or where the point where we're trying to calculate the field is like some distance b to the left of the right edge of the rod. Well, in that case, there will end up being cancellations from any values that are between basically L over 2 minus b, and at the right end of the rod's at L over 2, so minus b, and L over 2. So any points that are to the right will end up getting x component contributions canceled from points that are to the left. So that essentially means that if you're at the point x equals L over 2 minus b, then points between L over 2 minus b and L over 2 will get canceled by contributions, electric field contributions from points between L over 2 minus 2b, that is going from here to under the point and then another distance b again, so L over 2 minus 2b, and L over 2 minus b, which is the point directly under the point where we're trying to calculate the electric field. So again, if you don't believe that, then just plug in the endpoints and you'll see that at least those cancel. And since those cancel due to symmetry, then all of the points in between are going to cancel due to symmetry. So in other words, if we end up having our x value being less than L over 2, things still end up actually working out, because you can see that that's what ends up happening when you plug in that x value into the electric field equation, or at least the differential version of the electric field equations. You end up getting cancellations in the I direction from those corresponding terms. All right. Anyway, so it's kind of an abstract argument, so you might want to go over it repeatedly or just check the math for yourself to make sure that it works, but it turns out it does work. So now, time to deal with the integration. So this is a vector valued function, and it's going to be best for us to look at integrating the parts separately. There are two reasons for this. One, that'll make it so that the actual real steps fit on the slide, and two, because the type of integration that we're going to need to do for the x component is quite different from the tricks that we're going to need to use to evaluate the integrals in the y component. So let's get to it. First term is going to be the x component. So just as when the numerator of an integral is a sum, you usually break it apart and handle the pieces separately. We're going to split this apart into our x and y components. So here's the actual overall integral. In fact, we didn't even need two separate integral signs here. But the point is, we're going to evaluate each of these separately on separate sets of slides in this video. So, first, the x component. How do we deal with this x component? Well, here's what I notice. I notice that in the numerator of this, I have this x minus x prime term, which includes my integration variable, which is x prime, because after all, we renamed our axes the x prime and y prime axes because the point where we want to calculate the electric field is called x comma y, and we didn't want those to have the same names as our axes. So the axes are the x prime axes, and we have this term x minus x prime in the numerator, and we see that same term to the second power in the denominator. So that sounds like a u substitution type of thing. In fact, it turns out the easiest u substitution to make here, since taking a du is going to just completely eliminate this y squared, is to say that u is going to be equal to this entire denominator, except we don't want to raise it to the 3/2 because that'll make it more difficult for us. But we're just going to let u be that whole denominator inside of the parentheses. So x minus x prime squared plus y squared. In other words, we're letting u equal r squared. So that means that du is going to be negative 2. In other words, we need to find du so that we can figure out how to relate this dx prime, because once we make these substitutions, we're not allowed to use x prime as a variable anymore. So we figure out what du is. Well, du is going to be, well, take a 2, and that's going to be times x minus x prime. The y squared goes to 0 because that's a constant term. But don't forget about the chain rule. Take the derivative of the inside here. The derivative of the inside with respect to x prime is negative 1. So we end up getting a negative term out there as well. So there's du in terms of dx prime, which means that x minus x prime times dx prime, oh, I see that in the numerator here, that's just du over negative 2. That's good. So I'm going to turn that into a du, bring that over negative 2 out front, and we simply have our denominator u to the 3/2, which is just there. That's a polynomial. Now, what about our integration bounds? So we had been going x prime from negative L over 2 to L over 2, and by the way, I always recommend putting your integration variable along with your lower integration bound when you have a definite integral. It's a very good practice. It will alleviate a lot of confusion on the part of the grader, and you don't want your grader to be angry with you or confused about what you're doing. And it will also eliminate a lot of silly mistakes that people tend to make. So, by doing that, I realize, okay, now what is u? I'm going to put my bounds in terms of u as well. I don't have to, but I want to. So what is u? So if u is x minus x prime quantity squared plus y squared, well, if x prime is negative L over 2, I plug that in there, I get an x plus L over 2 squared plus y squared. And if x prime is L over 2 up here, I plug in an L over 2 there, and I get an x minus L over 2 quantity squared plus y squared. So those are my new integration bounds if I'm integrating with respect to u, and I'm going to substitute in with respect to u. So here we go. And here's the thing. I'm allergic to negatives. I don't like negatives, so I try to get rid of them when I can. So what I'm going to do is I'm going to switch my integration bounds. And by switching my integration bounds, I'm going to get rid of this negative. By the way, you also might be wondering, why didn't we just let u equal x minus x prime quantity squared? That would have been perfectly valid as well. That would have gotten rid of that x minus x prime term in the numerator, and we would have had the numerator in terms of du as well. But if we did that, our denominator would look like u plus y squared to the 3/2, and u is our integration variable. So in order to get rid of that, we would have to do a trigonometric substitution, a different type of substitution. If that sounds scary, well, it's a little harder than u substitution. It's just another trick, an extremely useful trick. And it turns out we're actually going to have to do that with the next integral anyway. But we don't need to do that here. So anyway, since I'm allergic to negatives, I ended up switching my integration bounds and absorbed the negative sign by doing that. That's perfectly legal. But then when I integrate, I end up getting another negative, so I probably could have just switched them back, but I will later, you'll see. But anyway, this is u to the minus 3/2 in the numerator. So taking the antiderivative of that, that's going to be u to the minus 1/2, raise the power by 1, divide by the new power, divide by negative 1/2. So 1/2 divided by negative 1/2 is a negative 1, so that's why I ended up getting another minus sign right there. And I'm going to evaluate it using these bounds, the same bounds that I have before. And this is already in terms of u, which is great. So there we go, time to evaluate it. And when I evaluate it, you're supposed to plug in the top term first, and then plug in the bottom term, and then subtract the two after plugging in the bottom term. I kind of did that, except I also absorbed the negative and did it in reverse. So that's why it looks like this, and you have the one with the minus first and the one with the plus second, because I ended up running the negative through. Okay, great. So there's the x component of our electric field. And, well, does this work for certain obvious situations? In other words, we know that if we're in the above or below the middle of the bar, the x component should be 0. Well, okay, plug in what the x value is above or below the middle of the bar. That would just be x equals 0. If you plug in x equals 0, you get just a negative L over 2 squared. The negative goes away when you do that, plus y squared down here, and 1 over the square root of that. And you get the same thing in the term on the right as well. And they're subtracted from each other, so they would end up canceling. So indeed, that tells us that the x component is 0 if you're right in the middle of the bar. What if your x component is positive? Or sorry, what if your x field value is positive, if your x point is positive? So if your x point is positive, you would expect that by symmetry and cancellations among part of the bar, or all of the bar, or none of it, depending on what the value of your x is, you should get that your x component for the electric field is positive. Well, is that the case? So if x is positive, that means that we're subtracting something from x here, and we're going to end up squaring that. So that's a small term squared plus a constant, and 1 over a small term squared plus a constant is a big term. And then in the next situation, we have that same value of x, but now we're adding an L over 2. Again, x is positive, so that's going to be a big term squared plus a constant. 1 over the square root of a big term squared plus a constant is going to be a small term. So indeed, we have a big term minus a small term, well, bigger term minus smaller term, leaving us with a positive result for our x component of the electric field. In other words, it checks out logically. So that's often a good idea to do if you have the time to check your work. Make sure that reality checks out. You could simplify this. I don't recommend it. I would just leave it right as it is, especially since you can see the fact that it behaves as expected for different values of x. What about the y term? The y component of our electric field, I should say. It turns out that's harder, because if you're tempted to do this u substitution right here, say, oh, let u equal x minus x prime, or let u equal x minus x prime squared plus y squared, or anything like that. Well, in that case, especially trying to absorb it in the whole denominator, nothing is going to change. Either you will end up getting extra terms that you can't deal with in the numerator, or you haven't really made it all that easier on yourself. So instead, we're going to do a different type of substitution. Instead of letting u equal some function of x, we're going to let some function of x, in this case, or I should say u equals some function of x prime, we're going to let some function of x prime equal something else that is itself a function that turns out to be easy to deal with. We're going to let x minus x prime equal y tangent theta. So we're going to let x minus x prime equal y tangent theta. That's going to be the trick that we're going to do here. This is what we call a trig substitution. And trig substitution is an extremely useful integration technique, and I would say that it's used almost as often as u substitution in a lot of physics and engineering problems, real-world problems. So my opinion is that if you're going to learn u substitution, you probably should learn trig substitution. Otherwise, you're probably going to end up going into a field where even u substitution, or calculus in general, isn't going to be useful anyway. So, unfortunately, the National AP Calculus BC curriculum dropped the requirement that students learn integration by trig substitution. I find that to be quite tragic, but luckily our hero BC Calculus teachers at our high school have put it back in anyway, and they're teaching it, so a lot of people already know it, which is great because, as I mentioned, it is extremely useful. Okay, so here goes. We're letting, as I mentioned, we're letting x minus x prime be y tangent theta. Why y tangent theta? Why not y sine theta or y cosine theta? Well, here's the thing. When we let it be y tangent theta and we end up getting the squared acting, we have a y squared tangent squared theta plus y squared, which means after you factor out a y squared from that, you have 1 plus tangent squared theta. That's a trig identity. That's equal to secant squared, whereas 1 plus sine squared isn't really equal to anything significant, and 1 plus cosine squared isn't really what we need either. So letting it be y tangent theta turns out to be extremely profitable here. In fact, that is often the case when you're trying to deal with something squared plus a constant. Remember, in this case, y is a constant. We're integrating with respect to x prime. So we let x minus x prime be y tangent theta. Great. So again, once we deal with that, we have a 1 plus tangent squared theta, which is called secant squared theta. So it turns out that makes our denominator very easy to deal with. But that comes at a cost. We've got to deal with this dx prime in here. So okay, if x minus x prime is equal to y tangent theta, that would mean just rearranging that x prime is equal to x minus y tangent theta. So dx prime, well, the x part just goes away because, again, x here is a constant. The minus part, well, the minus sticks. The y part, y is a constant, that sticks. And tangent theta. So the derivative of tangent theta is secant squared theta. That's something that you hopefully learned back in kindergarten calculus. So now that you know what dx prime is, we can just plug it in. What about the bounds, though? Well, same thing works as before. To figure out what your new bounds are in terms of theta. Theta is now your integration variable. So in terms of theta, you imagine plugging in x prime equals negative L over 2. So the lower bound would become x plus L over 2 is equal to y tan theta, or x plus L over 2 over y equals tan theta, or theta equals the arctan of x plus L over 2 all over y. And same thing for the top bound, except it will be x minus L over 2 all over y, and arctand. So there's your lower bound, and there's the upper bound. So now we are ready to proceed to integrate, or proceed to evaluate, I should say, because we've already done pretty much the hard work already. Well, a lot of the hard work is going to be in some algebra, but that's something that you can do, supposedly. Although, as you probably know, a lot of times the algebra is harder than the calculus. And this is kind of an example of that to some extent. But you also need to know some calculus tricks, and they're good to know. So, here is our integral. And again, as I've mentioned before, I'm allergic to negatives. So I ended up getting rid of this negative sign at the, quote, cost of reversing my integration bounds. Well, that actually just means that the larger integration bound, at least for positive x values, is on the top anyway. So I like that, and I don't have any negatives staring me in the face. All right, so now what do we deal with? Well, we're going to factor out that y squared term as advertised from the denominator, and since that whole thing is raised to the 3/2 power, that becomes a y cubed when we really pull it completely out. And what about this 1 plus tan squared theta? Well, again, that's secant squared. Y squared over y cubed is 1 over y, and again, y is a constant, so we pull it out front. It's now in the denominator out front. Well, secant squared to the 3/2 power is secant cubed. So there we go. But secant squared over secant cubed is 1 over secant. Well, 1 over secant has a name. That's called cosine. And I know how to anti-differentiate cosine. That's called sine. So now we just have a sine and we plug the stuff in. Okay, so as a refresher from your pre-calculus class, how do you evaluate, say, sine of arctan of x plus L over 2 over y? So here's the idea. What is arctan of x plus L over 2 over y? It's the angle of a right triangle such that the opposite leg has the value of x plus L over 2 and the adjacent leg has the value of y. Okay, it's an angle, in other words, where those parameters are true. What is the sine of that angle? Well, the sine of that angle is equal to whatever the opposite leg of that triangle was, divided by whatever the hypotenuse of that triangle was. Well, we just mentioned what the opposite leg is. That's x plus L over 2. What's the hypotenuse of that triangle? Well, that's given by the Pythagorean theorem. In other words, square root of x plus L over 2 squared plus y squared. So that's what the sine of that is. And similarly for the lower bound. So we can evaluate that. And that I just gave the commentary already verbally. We're taking the sine of that angle. So sine of this is given right here. And for the other one, the x minus L over 2, you'll just have an x minus L over 2 in those terms. So now that we know that, we can evaluate the whole thing. And there it is. This is the y component of our electric field. And now we're done. We can just put our answer in its final form. E vector is equal to e sub x I plus e sub y j, where e sub x and e sub y are the terms that we have just evaluated. So that is how we can deal with a vector-valued function in calculating the electric field in a two-dimensional situation, or at least even though the charge distribution was itself one-dimensional, we picked a point that was arbitrary in the xy plane. And now we know the electric field in that situation. Now, again, in general, on a test, or on a homework quiz, or on a final exam, you will have an integral table that you'll be allowed to use. On the AP exam, they provide you with a much less extensive integral table than what I provide my students. What does that mean? It means that they're not going to have to evaluate integrals that are as hard. Well, that's great. Make the practice harder than the actual game. So anyway, you might wonder why we didn't factor out those terms in the denominator and try to cancel the denominator. And if we had, so as to cancel the numerator. And the answer is that if we did that, we would have destroyed the knowledge of the possibility that the numerator could be negative. It's a similar type of argument that we mentioned in a previous video where we did not say that the square root of x squared was just x. We kept it as square root of x squared because we did not want to destroy the knowledge of the possibility of x being negative. And by saying square root of x squared is x and then canceling an x from the numerator. It works as long as you're in the first quadrant, but otherwise it might not work. Okay. So, in any case, you might, again, think that you're never going to be able to do something like this, but again, you're going to have an integral table at your disposal. And also, keep in mind that even if you didn't have an integral table, or if you didn't know how to use it, on the AP exam, and generally on my tests, the points, the great majority of the points are not given for the math. The great majority of the points are given for the physics, setting up the integral correctly, identifying what the point is that's going to contribute to your infinitesimally small electric field element, and how to express that correctly. That's where you're dealing with points. But actually evaluating the integral, it's like, 1 or 2 points. Sometimes none, depending on the problem, and depending on the year, and how badly people do on other parts of the problem, of the test and problem that year. Okay, and of course, as we mentioned before, when you plug in x equals 0, the x terms cancel, and all you're left with is the y term. What about the y component of the solution? Well, when you plug in x equals 0, you end up getting that the y component ends up eventually simplifying, and you end up getting this scenario. Well, that's kind of interesting. After we factor out a suggestive term in our denominator, we get a 2k lambda over y times 1 over the square root of 1 plus 2 over yl, or 2y over l squared. Well, in that case, First of all, this matches the actual result that's in the textbook when you plug in what lambda is. Second of all, you can see that in the limit as y becomes much greater than L, you end up getting that the e sub y term is 2k lambda, goes to 2k lambda over y, which is another known result. It's a result that we will get again in the next unit when we discuss Gauss's law. And that's just showing that right here. The limit as L goes, or sorry, this should say the limit as y goes, well, yeah, okay, my bad. I should say the limit as y goes to 0 or the limit as L goes to infinity. So I shouldn't have said that as y gets really big. I meant that as the bar gets infinitely long. As the bar gets infinitely long, we end up approaching this sort of limiting behavior. In other words, yeah, as the bar gets infinitely long, the electric field is not infinite. It actually has a particular value. So that's kind of cool. And again, that's something we're going to derive in the next unit from Gauss's law. Now let's look at a more typical example. This has shown up on the AP exam before. So determine the x and y components of the electric field at the origin when you have a curved bar of charge, in this case, in a quarter circle. And we're dealing with a plastic rod with linear charge density lambda. We'll assume that it's constant. If it's not constant, then you're just going to have to leave your answer in the form of an integral, most likely. But in any case, we should first notice that if it is constant, due to symmetry, the x and y components should be the same. So let's first write out expressions for the x and y components, and then slap integral signs in front of them, and then evaluate those integrals. Okay, so here's the idea. At some angle theta, depending on which charge element we're looking at some random angle theta, the amount of charge in the region d theta is going to be equal to, well, lambda times ds, where ds is the amount of distance that dq takes up. Well, what is ds? ds is dependent on the radius of the quarter circle. ds is equal to r d theta. So the amount of charge that's there is going to be lambda times r d theta. So now we know what this should say k dq right here. But so dq is equal to r lambda d theta. And notice that in this case, the distance from the charge element, it's constant. Because after all, this is a quarter circle, and we're evaluating this at the origin. So that means that little r squared becomes a big R squared, where big R is a number. It's whatever the radius is. So that makes things easier. What about the unit vector? Well, you can convince yourself that for any angle theta, the unit vector from any point here is going to be cosine theta I plus sine theta j. In other words, just think about how those angles go. It'll be cosine theta I plus sine theta j for any value of theta. And obviously that is a unit vector because square root of cosine squared plus sine squared is 1. So that part works out also. So there's our infinitesimally small electric field element, our infinitesimally small electric field element. And again, if you're not convinced about that theta bit, keep in mind the opposite interior angle theorem. You could imagine a horizontal line going down here toward where our charge is, and that would also have an angle theta along this R line. And so the adjacent part of that triangle would be r cosine theta, the opposite part would be r sine theta, and so the actual vector would be r cosine theta I plus r sine theta j, and of course the length of that vector is going to be r, so divide out the r's, and that's how we get our unit vector, in case you weren't convinced from that before. But you've probably come across that when you first encountered polar angles, either in Algebra 2 or pre-calc. So here's our dE expression, which is actually the answer to part A of that problem. So this is the arbitrary electric field due to a particular little bit of charge at angle theta. Now, what about integrating that? So we slap an integral sign in front of it, but in this case, we notice that first, like, okay, let's just evaluate the x component. The x component, well, we have a cosine theta there. We're able to cancel a factor of r. The integral of cosine theta is sine theta. So that's great. I know how to integrate sine theta. And then for the y part, we have, again, a factor of r cancels, and we have an integral of k sine theta d theta over r. And that's great because I know how to integrate sine theta. So those are our electric field components in integral form. Now it's time to evaluate the integrals. So for the x part, well, integral of cosine theta is sine theta. Plug in pi over 2 and 0, so that part's easy. So we just get a k lambda over r. And for the y component, well, integral of sine theta is negative cosine theta. It's like, oh no, a negative. Well, here's the thing. Cosine of pi over 2 is 0. So then you're going to be doing a negative thing with a minus. So you're going to get a double negative, and those end up canceling. So you have a minus cosine theta. Well, first term is 0, so you're going to have a 0 minus. Well, cosine of 0 is 1. And so you end up getting a 0 minus negative 1 on that, and you get a k lambda over r. And just a reminder, it was a negative 1 because, well, the first negative ended up coming from the fact that you're subtracting the different values, and a negative 1 because it's a minus cosine of 0, so a minus 1. So k lambda over r. In other words, our intuition turned out to be correct. The x components and the y components turned out to be the same. So, with that in mind, this is the final answer to our electric field, k lambda over r times I plus j. Now you might be wondering, why didn't we do this example much earlier? After all, this was easy. At least compared with that stuff we were doing before with the bar of charge and finding the electric field at an arbitrary point in the xy plane. So why didn't we do this before that? The answer is because here we had a two-dimensional charge distribution. And that is going to provide us with some intuition for being able to figure out the electric field in general with two-dimensional charge distributions without necessarily having to employ multivariable iterated integral calculus techniques. And that's what we are going to get to in the next video. Until then, I thank you for watching, and if you have any comments or questions, or in particular if you have found any mistakes, please let me know in the YouTube comments. Thanks again.